slide, who is going to tell us about how to go from family forward homology to homological symmetry.
Thank you very much. It's a pleasure to be here, and I mean, formally I'm on the organizing list, but really the organizers were Ron and Tony, and I wanted to thank them. So, thank you. Family fluid cohomology and how to use symmetry. So the first thing I will describe is how to think about fluid symmetry without corrections. Corrections here means without homomorphic disks, which really means in this case, I'll think about complex manifolds with Lagrangian torus vibrations so that all the fibers are smooth. And I'll explain how this symmetry works on the manifolds. And then I will explain that this explanation that I gave, which already appears in the literature, isn't somehow, it's some technicalities that are not exactly done correctly. So we'll go back and we'll take a slightly different point of view on what was done. This will rephrase everything with some more sophisticated machinery. And finally, I will talk about the important part, which is somehow how to deal with the case where the singularities there are singularities. And this is still work in progress, but the main thing is that I claim that the singularities that are first singularities that you encounter, which are this related to this superpotential function. And the mirror picture, that in fact in these cases you don't need to think about singular Lagrangians, and you can replace all the singular Lagrangians that ever appear by inverse Lagrangians, and then use standard tools of Floer theory to address that case. So anyway, that's where we're at. And as an outcome, you can basically make sense of SYZ mirror symmetry for hypersurface symmetry. Okay, let me start. So take the symplectic manifold, and as I said, we'll look at the Lagrangian torus vibration with no singular fibers, and let's assume for now that there's no section, that there's a Lagrangian section. And then Stromberg and Zaslow in 96 constructed a complex manifold by taking the dual torus vibration. In fact, they studied this in general, but this is a special case where there's no difficulty, and you really produce a complex analytic manifold. We can just take this as a definition. X and Y are mirror if they're produced by this procedure. If you're curious about families, in this case it's fairly easy. You rescale the symplectic form on X, and that gives you a family of complex structures on Y. And in this setting, we'd like to prove homological symmetry. Really show that the final category of X is equivalent to category of Functor on Y. And there's a small problem, which is that if you take an arbitrary Lagrangian in X, then its Floer theory is just not defined over the complex numbers. So you could say, well, okay, let's not just try to do it one point at a time. Let's remember this family, but even that doesn't work so well in general. Working over this family would mean like you would have something over a power series. But the power series is not quite the right thing, because the exponent should be something like area of a homomorphic disk, and in general the areas are real numbers. So instead we replace power series by this bigger race. It's Homological field lambda. I don't know how to use this pointer. Anyway,
Green.
So this Novikov field lambda, which is you do just like power series, it's some infinite sums, which the exponents go to plus infinity, but the exponents are real numbers. And this is the field that we're going to work over. And what I want to point out, somehow, the thing that we're going to use is that it has this non-Archimedean valuation, which says take a power series and take the exponent of the leading order term. And then you can do, just like the complex numbers have this norm, which is just the norm of the complex number, you can use this valuation as a replacement. You can do analytic geometry with respect to this field, and that's how we're going to state our mirror symmetry results. So in particular, if you take lambda star to the end, lambda star is again the complement of the origin, that should play the role of the torus, of the complex torus. So ring of functions on that you expect to be Laurent polynomials. So I have Laurent polynomials down here. But in the world that I'm working with, we don't do algebraic things, we do analytic things. So instead of Laurent polynomials, we get some kind of Laurent series. But not, well, you can't multiply series which ends in two directions unless you have some additional properties. And the additional properties is that the series are required to converge at every point. What that says is that the valuation of the coefficients that appear have to go in a certain way. Okay. So, as I said, what we're going to do is kind of a local to global approach. So working on this big domain is just too difficult. But instead, what I'm going to do is I'm going to introduce some subset of lambda star to the n, which I'll call yp. So lambda star to the n maps to Rn by these variation maps that I said before. And then inside Rn, I pick up the subset p, and yp will just be the inverse image. So you can do this, of course, for arbitrary subset. But in general, the object you get here does not have any well-behaved, it's not well-behaved from the point of view of analytic geometry. What will give you a well-behaved object is if you assume that P is a polygon. And to make my life even easier, I will assume that it's an integral affine polygon, which means that when you draw it, well, let's say that the origin is here, just for simplicity. The facets are defined by some vectors, and these are supposed to be integral vectors. Okay, so in the lattice. Vectors in the lattice. But I don't require that these distances be integral. They're allowed to be any real number. So that's what I mean by an integral affine. So you have an integral affine polygon. You can associate the subset of lambda star to the n, and therefore you can look at those Laurent series, which, well, before we said Laurent are they should converge at every point, but now we can require only that they converge at every point here. That's less of a condition. So there will be more Laurent series that converge here than converge arbitrarily. So that gives you a ring, which I call gamma p, and this is what is called an affinoid ring. And just take it as a name. That's good enough for us. So we have certain Laurent series with convergence properties associated to this. Now, what does this have to do with mirror symmetry? So I've been going pretty fast so that we can actually say something about mirror symmetry. If you take the base of a Lagrangian torus vibration, then that has an integral affine structure, which means that near every point you can distinguish a collection. You can identify identify neighborhood of every point with Rn, and this identification is ambiguous up to GL and Z. Well, the points with Rn may be mapping the origin to Rn, and this is ambiguous up to this. So since this is the ambiguity, the notion of being a polygon, an integral affine polygon, is well defined. So then you take your space and cover it by such domains. Maybe that wasn't fine enough so that all the intersections are, again, integral affine polygons.
It's convex.
Pardon?
Convex polygon?
Yes, convex polygon. So, so each polygon has this domain associated to it. Whenever I have an intersection, I can glue these domains together. So then I get a space Y that is associated to my symplectic manifold X that lives over Q. And in fact, it turns out that Y also projects to Q by the valuation. Okay? Because remember, Q is locally identified with Rn. Yp lives inside lambda star to the n and has this valuation map. And so this is our original projection map. This is some analytic space with a projection to the same base. And this I would call either the rigid analytic SYZ dual or a rigid analytic T dual of the space X. And this is what we expect to be the mirror, well, up to some minor correction. So there's the first case. I think the first case this was considered in literature was almost simultaneously in work of Kaya and Consager Stogelman. Kaya was thinking mostly about K3 surfaces. Consager Stogelman were thinking about abelian varieties. So what they proved is that if you look at if you're in a situation where the mirror is a complex torus with abelian variety, then you can look at Lagrangian sections of this vibration, and the Floer theory of Lagrangian sections of this vibration recovers some kind of multiplication in the category. So these Lagrangian sections go to line bundles, and multiplication in Floer theory here goes to the product of sections of line bundles on the other side. But that's not what I want. I don't like this answer because it forces you to introduce some additional objects other than the ones that were intrinsic to the picture. The picture has Lagrangian torus fibers. And so I want to do everything just with my Lagrangian torus fibers and not require that I should have some sections. Why have some sections at all? And part of the reason is that describing things in terms of sections of line bundles works very well when Y is very nice productive variety, but in general, that's not going to work. So we need a different issue. So this is that's what family Floer homology. So now I'm going to impose an assumption, which is that pi 2 of q is 0. Oh, this works. So this is just to make sure that that the relative pi 2 of the fibers is 0, which means they bound no holomorphic lists, which means I don't have to go around keeping track of corrections coming from holomorphic lists. Just as a remark, I know of no example where q is closed and pi 2 is non-zero. It might exist out there, who knows. So Fukaya proved the following result. So if you take one of these fibers, then, as I explained, the nearby fibers, they correspond to some points. You can parameterize them by some points in this space. Oh, I brought it back. That's okay. So let's take one of these fibers, and let's take some arbitrary Lagrangian. So what Fukaya proved is that you can basically, if you do things carefully, you can recover Floer theory of this Lagrangian with a nearby fiber. Let's see what the terminology is. This is x lib p, this is x q, this is q, and this is p. Out of some construction that only uses holomorphic disks and holomorphic strips involving x, q, and l. And he kind of explained this in his talk. What I want to do is I want to state it slightly differently, the construction slightly differently. What I want to point out is that the point P determines, or rather, P together with a local system determines a point in this space Y, P, where capital P is now some kind of polygon that's big enough to contain these 2 points. So now, if I do Floer cohomology, the Floer cochains of F with this object, well, that gives me a vector space associated to this point, or rather a chain complex. To a point in my P. And the question is, how do these chain complexes vary as you vary the point around? And the answer is, these chain complexes are just fibers of coherent sheaf. So here it's stated slightly differently. So the way it's stated here is that, you can, instead of saying coherent sheaf, what I wrote is that there is gamma p is the ring of functions on the space. And instead of saying coherent sheaf, I just said there is a complex of gamma p modules. And instead of saying fiber, I said, if you take this gamma p modules and you tensor over lambda with gamma p, well, here when you tensor, you have to make a choice. And this choice of making lambda into modulo gamma p is exactly choosing a point. Okay, when you tensor with lambda, you recover Floer cohomology. So how did they prove this? Well, there's one basic idea, which is that you would like to make sure that the holomorphic curves that contribute to this discount, and the holomorphic curve, this differential of L with xp, and the holomorphic curve that contributes to the differential of x with x cubed, you'd like to make sure that they're the same. Okay? Because if they're the same, then you can imagine that there's a kind of a formula that just has this as a variable, so that the answer recovers the corresponding Floer group, and you plug in the corresponding values of your coordinates. Now, how to make sure that happens? Well, there's a very nice trick, which is you can just pick a symplectomorphism, pick a diffeomorphism that takes this fiber to this fiber. Just imagine moving everything to the left a little bit, or right a little bit, and preserve L. That's the case precisely because we've assumed that L is transverse. Now, in general, diffeomorphisms are not going to have anything, not going to give us any meaningful structure on Floer theory, but if P is sufficiently close to Q, then this diffeomorphism can be chosen so that it preserves the fact that the complex structure that you use is T. Well, whatever T means, it means that we can use it for Floer cohomology. So now you just, when you define the Floer cohomology of L with xp, you just use the complex structure which is obtained by pushing across this diffeomorphism. But then the disks agree on the node, but their areas change. And the fact that we get a module over this ring of functions is exactly recording how these areas change. So anyway, this is just a brief summary, a brief overview of the idea that Kenji essentially already mentioned. So now we have coherent sheaf on one. Okay? So what's our goal? Prove homological mirror symmetry, which means construct a functor from the Fukai category to coherent sheaves on the space Y. But Y is just obtained by gluing together the Y piece. So you can easily imagine that this construction, in fact, extends to a functor. Functor from Fukai category to perfect complexes on Y. Perfect complexes just means some chain level version of the derived category of coherent sheaves. Y is smooth, so you don't have to worry about this difference. And moreover, I proved that this is a faithful event. So I borrowed some language from Kenji. I said the proof is heavy. Okay, so it's just there's no. I'm going to explain. There's three ideas, and the three ideas already appeared in the literature. But to put them together is just no easy task, and I'm not going to do that. This is not the right conference for it. I would like some more.
To the left. Yeah.
Ah, yes, the wall is full of chalk. So the essential problem, first one you encounter, is that, so I have this thing here, and I've made this choice to make Floer theory with respect to this guy. But now, what about this? How do I define Floer theory with respect to this? I can't use the same design. But what I can certainly do is I can choose some Hamiltonian deformation of this Lagrangian, like this yellow one. And that allows me to do Floer theory. So let's call this guy Q1, let's call that Q2, and let's call this L1, let's call this L2. Okay? So the Floer theory of Q2 and L2 is well behaved. And in fact, it's well behaved in some neighborhood of Q2. There's a whole strip here. Floer theories with fibers, which I can do using the choice L2. But then for L1, there's some other neighborhood using that approach. But they intersect. Not clever. If I pick Q in the intersection, then you need to be able to relate the two Floer theories. Unfortunately, we have machinery for doing this. It's called continuation maps. We have the statement that Floer theory is invariant under Hamiltonian isotopes. But it's not invariant on the nodes. It just means there's some kind of chain map. L1, X of Q, let me ignore that, to CF star L2, that's XQ. And it's a chain, it induces an isomorphism on homology. If you come from algebraic geometry, this seems, sort of kind of classical point of view, thinking about the derived category, this seems like a nightmare, because this means that like every time that, instead of having isomorphism, we're trying to glue things via strict maps. I'm gluing things via something which is much softer than that. But for example, if we had 3 of them, then you would get 3 such maps. And the diagram would only commute up to homotopy. But the wonderful thing is that Floer theory gives you the homotopy. And that's what I'm saying in the second part about what needs to be done. Okay, you need to use a model for perfect complexes on Y, which is basically adapted for this technology. So you just build something which allows you to have a bunch of modules over these ring of functions of the cover, and then instead of trying to glue them together by strict isomorphisms, you glue them by quasi-isomorphisms and keep track of higher homological.
But it gives you all the coherences, right? Not just...
It gives you all the higher coherences. And there's a wonderful thing, which is that we're doing things in finite dimensions, which means that you only need n, finite linearly coherent states, because the cover has cohomological dimension n. And this is actually kind of a deep technical point here at some point where you really need to kind of shrink everything a little bit, but you only need to shrink things n times. So you're saved by finite dimensionality. Anyway, so once you have that, I'm not going to say much more, but there's now a standard machine for trying to prove that certain maps are isomorphisms. In this case, it happens to not quite give you as much as you would have hoped for. It gives you only injectivity. This is the Cardi relation. This is the thing that we saw in Kevin's talk, where you take this analyst with the Lagrangian boundary condition and you degenerate it. Well, he doesn't draw it like that, but he degenerates it like that. And the picture you should have in mind is that this is some kind of this has L in it, this has L in it, L, this is L, this is the fiber. Okay. Anyway, this is just sketch of it. And I just wanted to mention that you can do this even without assuming you have a section. If you don't have a section, then there's an obstruction to having a section. That's a class of H2 of the base, and then you can turn that into a class of H2 of the space Y, which coefficients in O star. That's a gerb, so you twist by this gerb and you get the same result. Okay, great. Yes?
What is the setting of
Here? Yeah, it starts out being nowhere. And then, I don't know what to say. Oh, no, yes, yeah, it's okay. No, this is not exactly it. Let me just make it. Thanks. Okay. So, now, yes. So now what I want to explain is, everything I said so far was without correction, without any holomorphic disks. So let's now try to do some kind of more adult version of trying to understand this fuzzy mirror symmetry. Well, the first thing that people should know about when you do a fuzzy mirror symmetry is that you have some singularities. Let's use some 10 degrees of case surface. You have some singularities, and in dimension 2 at least, what we know is that generically, these Lagrangian fibers do not bound any homomorphic disks, but there are some kind of walls. And along these walls, there's a homomorphic disk, and these walls propagate in some complicated. Okay. So I want to break up the problem into two parts. First, we should understand what happens away from the singularities. And that doesn't mean ignoring the walls. I mean actually putting all the walls in. And then we put the singularities back. So that means we should think about Floer homology when there are homomorphic disks. And then this is also a result of Fukayev in 2009. This is his Analytic Convergence paper. And he says, you take a Lagrangian, and I'm going to assume it's a torus to make life simple. Then you'd like to describe the Floer theory. So this is something here. Some space with some Lagrangian. Some Lagrangian torus. And then you'd like to understand the Floer theory of the nearby Lagrangian tori. You know something about sublective topology. The nearby Lagrangian tori are parametrized by first cohomology because of this flux map. And, well, let's assume this polygon is sufficiently small. On the other hand, since this is a polygon in H1, we can associate to it the space YP, which lives in lambda squared. And what Fukayev proved is that on this space YP, there is a bivector field. There's a section of, there's elements of H0, Y coefficients into H2 and T, with the following property. Wherever this bivector field vanishes is exactly wherever the Floer theory is well defined. Now, I'm assuming Calabi out. That's why I said mass locking net is 0. So, how to interpret this geometrically? Geometrically, this means that the mirror space, or the local mirror space to Y, is YP, non-commutatively deformed by alpha. That's what it means. Although, of course, it doesn't prove it. It just tells you that the points of the space, the points that survive the non-commutative deformations, are the ones you would have expected if this was the answer. Okay. So what I wrote there is that this tells us that we should take such pieces as our local charts, and then we can should glue them together. So let's go back to the setting where this L is not just an arbitrary Lagrangian torus, but actually a fiber. It's a Lagrangian torus fibration. You can proceed the exact same way. You have some significant difficulty in proving that, before I said, take P prime inside of P, then you immediately get an inclusion YP prime inside of YP. Okay? But in this setting, this YP is, everything is not, the coordinates are not canonically defined. So what you really should say is that if you take two overlapping charts, then you'll have some kind of holomorphic map between the two pieces that you've defined, between these two YPs. And these holomorphic maps will intertwine these two bivector fields. So still, you can use this construction to glue together a global space, and that global space will have a bivector field, and that is, well, that's an open part of your field. That's this thing I call Y0. Okay. So this is, yes?
Yeah. So you said it doesn't prove that it's that deformation, but what did you mean? Did you take the canonical quantization, or?
I will explain in a second.
Okay.
So right now, all I can say is that this is the suggestion you get, and then I will explain that there is actually a specific non-commutative ring that Floer theory will tell you that you should use. So I'll tell that. We don't have to appeal to deformation quantization or anything.
But
Floer theory will give us an answer.
Whatever that answer is, it's infinitesimal is alpha p. Does it have any higher order terms, or
It's so it's the way I will set it up. It won't have any higher order terms, but that's because everything is hidden in the formalism of Floer theory. I don't exactly know how to answer your question precisely. So I don't know how to answer because I don't know the algebraic literature of how to construct these rings. I just know how to construct them out of Floer theory. So it'll be a good question, but I. Okay, so anyway, we get this space Y0, and it has this non-commutative deformation. And here I want to mention Julian Tuesname, who had this slightly different, I think, maybe more convenient formalism from the point of view of building homological algebra, where he treated this space as basically a space together with a family of Marquardt elements, the holomorphic family of Marquardt elements. That was his contribution to this. Okay, so if you have this, now we have this. So since we have this, what's left to do? Well, first thing we need to do is we need to extend across the singularities. Okay, good. This is the open part. We need the whole space. I'm going to talk about that at the end. The next thing we need to do is construct a mirror functor. I gave you some idea for how you construct a mirror functor, but again, I'm going to suggest that there's a slightly different way to do it, which will be better equipped to handle these questions about what to do in non-commutative case. And finally, we need to prove that the functor is an equivalence, but for that, again, we have an idea. We should just try to run these Cardi Relation. Okay, so now second part of the talk. What kind of Floer theory should we do to handle this non-commutative story? So I have to remind you that the objects of the Fukui category are Lagrangians with unitary local systems. So that means is representations, I mean, for the complex numbers, it's just S1 values representation of the fundamental group. Over the Novikov ring, I have to replace S1 by the unitary elements. The unitary elements are the elements of valuation 0. So that means our series whose leading term has no power of t, like t lambda equals 0, and has non-zero coefficient. So that's u lambda. Now, non-Newtonian local systems are bad because you have convergence problems. Okay? But so this formulation is a little bit, one way, I'd like to formulate this, instead of saying I'd like representations into this thing, I'd like to say I'd like representations into lambda star. But instead of saying representations of the fundamental group, I'm going to make my fundamental group, my group ring, well, that's the same thing as representation of the group ring. I'm going to make my group ring bigger. I'm going to introduce something which if I, R L. So this is some completion of the group ring, and it's just the completion with respect to the t-adic filtration. This means instead of, in the group ring, we have elements like this. Okay? And now I want to allow infinite sums, but I want to allow infinite sums as long as there's only finitely many terms below which have valuation less than any given quantity. And I claim if you look at maps from here to here, that's exactly unitary representation. Just a different formulation. Yes.
You may have said that, but I may have missed it. Is L a K pi 1?
Good question. You could do this with any L. Okay. This doesn't give you a good theory for any L. If it's not a K pi 1, you will replace the group ring by the chains of the base group space. Okay. But we're talking about tori, so I don't want to talk about that. Okay, and so now I'm going to talk about an enlargement of the Fukui category, and I think of it as some kind of formal enlargement. And you'll see in a second why I call it formal. And in which I take my Lagrangians, And instead of saying with unitary local system, I want to take the arbitrary representations of this completion. Okay? Because that's what I think of as infinite rank unitary local systems. Okay. So there is a canonical universal module over this ring, which is this ring itself. So let's consider it. Great. So this is, I claim that this corresponds to the structure sheet of this thing called Y0. What is Y0? Well, before I said if you take P inside Rn, you could consider Yp. Okay? But of course, you can just take the point. If you work out what this is exactly U lambda to the n. This is the structure sheet of the unitary elements. Okay? So instead of taking the unitary elements one at a time and computing Floer homology between them, I integrate over all of them, which means that I take the structure sheaf of that variety. Well, it's not a variety, but anyway, rigid analytic space. So I said, so anyway, that explains this claim that this is topological, because on one side we're taking a completion of the Laurent polynomials, on the other side we're taking the completion of the group ring. The group ring of the fundamental group of a torus is Laurent polynomials. So you just have to check that the completion is the same. But to actually be precise, you have to check that the X groups are correct. Okay? And this actually requires some care. And well, it requires knowing how you're going to define the category of sheaves on this space Y, and more importantly, how you're going to handle the structure sheaves of components. Of affinoid domains. So if I take Yp inside Y, then I can take the structure sheaf of the domain, and I could try to consider it as a module, as a coherent sheaf, not coherent, as a sheaf on the whole space. It's not coherent. That's the whole point. Now, if we were doing algebraic geometry and I had like an affine subvariety, then this push forward would be quasi-coherent. Okay? But in analytic geometry, you can't quite do that. Well, usually you can't quite do that. But I don't know if Maxime mentioned this in his talk, but there's a way to do this by keeping track of the topology of your vector spaces at all times. So when you define X groups, instead of defining them as Homs of some, instead of defining them as Hom of vector space, instead of defining them as cohomology of some complex, which in that complex you're going to use linear Homs. Instead, you use the topology that comes, use the t-adic topology throughout to define the X groups. So if you do that, then what you get is that the structure sheaf, if you take the structure sheaf of this component with itself, and you try to compute this group, you actually just get, you just get gamma 0 back. You get the ring of functions on the open domain. This is slightly surprising thing. But it's not too hard to see once you just you remember the fact that this ring of functions gamma 0 is just a completion of the ring of functions gamma itself. So you just get some formula in terms of completing the ring of functions gamma. So here's the right answer. Okay, so you can now do the same thing on the symplectic side. I'm going to define the Floer, how would you define the Floer cohomology of this? RL means the Lagrangian RL hat, the Lagrangian L equipped with this local system. How would you compute this Floer cohomology? Well, it's going to be the same as the cohomology over, if there's no homomorphism, cohomology of L with coefficients in this Hom space. Here, I take Hom over lambda, but of topological vector spaces. And if you do that, then you can reduce it to the case where you do the completions around, just the completion of the one with the completions. And this isomorphism actually is non-trivial. This is called well, it has a hideous name. It's called the convergence of the Islandberg Moore spectral sequence. Nobody seems to have come up with a better name for it, but it's shown up in topology before. And so at least there's some, computation on both sides which agree. So that's one domain. Now we need to figure out how to glue them together. But of course, what I've done so far is my domains are just points. Okay? So this cover that I've said is just a cover where you take Y and you write it as a disjoint union. Well, maybe that's a bad name, but anyway, over all points in the base of Y. Okay? This is a bad cover. You can't use this cover for any practical purposes. What do we need to do? We need to flatten out these points. Well, flattening out these points is exactly this. Is how we are going to reinterpret family Floer cohomology. So, So now I introduce some notion which I call analytic completion. That's why the other one was called formal completion. So let's pick a norm on the first homology. And before I said I should allow myself all series with the property that the valuation goes to plus infinity, as g goes to infinity in the group. But now I introduce an additional term, which is that I can multiply that by epsilon, some quantity, times the norm of my element, of my fundamental group, which is the same thing as H1 in this case. So what does that do? Well, what you should keep in mind is that this quantity is always positive. So what you're allowing is there are more series which are allowed, as epsilon gets larger, there are more series which you are allowing. But in practice, what is happening is you are shrinking the corresponding domain. This exactly corresponds to what I said earlier about there's Laurent series. Sorry, there's Laurent polynomial. Inside Laurent polynomials, we have this ring, gamma p. I'm sorry, no, it lives inside gamma p. And if I have p contained in p prime, then then I have this inclusion like this. So every single step you complete further and further. At the very end, the most natural thing to do is to do gamma of just a point. And this is the thing that corresponds to the ring of functions on the unitary element. Okay. So now we reinterpret this result of Fukaya, but family Floer cohomology. And it basically says that you can do, if you take another Lagrangian, okay, then you can do Floer cohomology with a pair, K, with this analytic completion, as long as epsilon is small enough. That just says, that's exactly what it's saying. And then, well, once you see that, you can basically believe that the functor that we built before, which was some kind of ad hoc construction of this functor, it's now just a Uneda functor, in the sense that you build a category in which, I'll just call it f hat epsilon. And inside this category, you have f of x, your usual Fukaya category. But now you can have one more object. You also have this object, which is, I'll think of as epsilon. And you can do the Uneda functor of this with this. From these objects to these objects, that gives you a map to modules over this, and that's our functor, our local family Floer function. Okay, so now you just imagine that we solved the problem. We solved the local problem, so now we solved the global problem, which means that instead of having just one of these, we have one such object for every element of the cover. So I'm going to make a slightly different terminology for this. This has a U in it. So U is a cover of Q. And if you take a cover of Q, so in particular you get a cover of Y. Okay? So now the structure sheaf of the components of this cover. So this is something that lives in the category of modules, O modules on Y. Okay? And I will call this category OU. Great. So the computation that I did about this completion being the same as the completion that shows up in when you complete the ring of functions, i.e. the fact that this R hat epsilon L is basically the same as gamma P. That tells you that you have this inclusion functor of OU, of this category O of U, inside this completed Fukaya. And so then you apply a Uneda functor, and that's our global family Floer functor. But this setup has one advantage over the previous setup, which is how would you prove that the functor from here to here, that the Uneda functor is fully faithful? Well, you just need to prove that every object here lies in the category generated by these. Okay? And that's what the proposal is. I haven't quite done the details, but the claim is that if you look at this category, it's actually split generated by the objects here. Therefore, everything maps to here injected. Fully faithful, that this functor is fully faithful. And now you'd like to generalize this a little bit, and just like I said, the story that I've been telling you has no correction. So how do you do this with correction? Well, it should work out the same way. And now the following wonderful feature comes out, which is that Floer theory tells you that this object object R at L, let me just do that for now, is always unobstructed in the Clavier case. Okay, so there is a canonical non-commutative deformation of the ring of functions, which is determined by the symplectic geometry. I don't know how to pin it down. I don't know how to tell you what it is from the other side so you can compare it, but it exists. So,
Well, when you say determined by the symplectic geometry, you really need to look at the adic family of your symplectic manifolds. Which adic family are you taking? Are you just rescaling the symplectic form, or?
well, you could, if you want. I mean, the one parameter family is always rescaling the symplectic. Now, you could make a larger family by introducing bulks, but I haven't.
Okay.
But yeah. So then you can repeat the same story. This O of U gets replaced by a corresponding non-commutative thing. And there's a little bit, I believe there would be no issue in proving the generation, but actually proving that this gives you the right answer that you would expect from the algebraic side. That is, that you are gluing these non-commutative rings correctly. That should require some tools of homological algebra. And Kenji talked a little bit about, I'm sorry, not Kenji, Maxime Pitavia talked a little bit about this in his first talk. I don't have much more to say. Okay, now, we'll talk something completely different. We're now going to do some geometry. So, remember that so far everything has been about this open part, only about the smooth fibers. So, that means that there are some objects that are missing from Fukada category, which are exactly the things that correspond to the singular object. So there's actually a very simple toy case of this, where you take C2, and I'd like to think of C2 as mapping to C by the map XY. This has a single critical point, and the fiber over generic point is a cylinder. And I want to remove one fiber from this. I think we'll remove this fiber.
So what's the category? So the one point
I don't think in terms of, I'm sorry, I don't know how to think in terms of this, what do we call it, skeleton or whatever. I'm going to talk about XYZ vibrations.
Produce equivalent category.
Yeah, probably, but I don't know how to think about it. There is a skeleton here floating around. So, this is a Lagrangian torus vibration. So let's call this X. There's a Lagrangian torus vibration. X over R2 with a single critical point. Okay, this is slightly confusing. See, this is C and this is R2. -1. So how is this Lagrangian torus vibration produced? I don't want to go too much into the detail, but roughly speaking, you take a circle in the base, you take a circle in the fiber, and you move the circle in the base and the circle in the fiber around the circle in the base. So that's the family of Lagrangian tori. And I want to point out that there is exactly one singular fiber, which is that one singular Lagrangian torus, which corresponds to when you over 0, there's one singular point. And there is a single circle here that collapses to that singular point. That's called the vanishing cycle. So the parallel transport of the vanishing cycle over the circle of radius 1 is singular. It looks like this. And if you do mirror symmetry, it means if you try to kind of just do SYZ duality, it works out perfectly, except that on the mirror side, you get, so you start with C2, you start with C2 minus XY equals 1. Okay? That's this total space. And then claiming it has this Lagrangian torus vibration. When you do the story, you dualize it, you get lambda squared minus UV equals T. Notice it looks exactly the same, except that I set 1 equals to T. But there's one point missing, which is 0. Okay? And the claim is that this point that's missing, this 0 point, is exactly this Lagrangian torus. Okay? And so this was announced in 2009 by Fukaya. Now I put question mark, because it hasn't been written yet. There'll be further results that of the same nature. This is the only one with Fukaya's name on it, so I felt it was okay. So anyway, so there is this immersive Lagrangian, and it represents the missing object. And moreover, he made a stronger claim, which is that if you can do family Floer cohomology and patch the chart near this point with the nearby charts of the Lagrangian tori. And of course, he did it in the formalism of like the first third of my talk, using the old point of view family Floer cohomology. And I think one of the things that really needs to be done is understand the story that I didn't really explain. I mentioned about chains on the base group space or group rings, how to do it with immersed Lagrangians. But I think that's doable. Just, I don't want to talk, I don't have anything to say about it. Great, so let's go up one dimension. We take C3, and you can do the same thing. So you can just go around here and just replace this 2 by 3 and replace this thing with a further variable, so that it is C1 to 2 to 3. Okay, and it looks exactly the same. There is exactly one singular fiber, except that now the singular fiber is a little bit hard to draw, but let's just do it like this. I don't know if it's maybe that's not maybe that's suggested. So the singular fiber is exactly the fiber over 0, which is the union of the hypergroup. And you can build it, and the general fiber is T star T2. Now T star T2 has plenty of Lagrangian tori. If you take these Lagrangian tori, you can move them around the base, and you get this Lagrangian torus vibration. And this goes back to work of Gross in the late 90s, and then his students, Patesi and Castanio Bernard, they then worked on this, and then Denis and I had some further work. And anyway, what you can extract from this is that there is an expansive vibration. If you try to dualize it, and you look only at the open part, what you get is, so inside lambda squared times lambda star cubed, you look at the conic bundle over lambda star cubed, which degenerates along the locus y, along the locus y1 plus y2 plus y3. Okay. So this is sorry, oh yes. Oh, I did something a little bit off. I should set y3 equals to. I should set y3 equals to 1. Okay, there's something wrong with the slides, and I don't have time to fix them. So just replace y3. So the thing lives actually lambda squared times lambda star squared, and the correct equation is uv equals y1 plus y2 plus 1. That's the right equation. Sorry. Anyway. But if you only look at the smooth Lagrangians, you're missing the locus. You're missing the locus where uv equals 0. Okay. Now geometrically, so that's what we need to do. We need to fill in uv equals 0, and there's evidence for this, which is that with Denis, I basically proved that the derived category of coherent sheets on this full space Y, which is the thing you get by filling in uv equals 0, it embeds in the derived category events. So we need to find some way of putting in these missing objects. If you think about immersed Lagrangians, you get all the objects that correspond to the solutions where the valuations are non-zero. Again, you have to do y1 plus y2 equals 1, where the valuation is non-zero for either y1 or y2. But then there will be some solutions where the valuation of y1 equals 0 and the valuation of y2 equals 0. So these are called, should think of as the unitary solutions, and those are the ones that are missing. Okay, so that's the results. So me and I really proved this last year, but we haven't sat down to write it, and I don't know when we will sit down to write it. The claim is that there is actually an inverse Lagrangian torus, which actually represents these objects. It doesn't represent them, these spectral sheets of points. It doesn't represent them directly. It actually represents the direct sum of the structure sheaf of the point with its shift by 1. How do you produce these Lagrangians? Well, you see there's this direct sum of this plus this. So the intuition is you start with this. So now I'm back at C3 minus Z1, Z2, Z3 equals 1. Okay? And you can easily write down this inverse Lagrangian. This singular Lagrangian. That's this. And over here, it passes through the most singular point of your variety. It passes through here. If you choose it to pass through here, then you get something immersed, and you're okay by Kenchi's work. Okay. But if you do it there, then that doesn't work. So now I'm kind of already hinting at the answer. If I'm telling you that what you're supposed to do is take a direct sum of 2 of these, and we think that somehow this object is the right one, then what we should do is we should just take 2 copies of it. And you take 2 copies of it, and then smooth here. When you take 2 copies of it, there's 2 ways of getting rid of singularities. If you do it naively, you get the 0 object. You shouldn't do that. You should do it in a smart way. If you do it in a smart way, you get this. Now you could say, how do I see this equation? y1 plus y2 plus 1 equals 0. Okay? Well, you see this equation because if you think about the local systems on this Lagrangian, so local systems on this Lagrangian, this would kind of be, it's a rank 3. So there's 3 parameters. But there is 1 parameter in the base and 2 parameters in the fiber. 1 in the base, 2 in the fiber. Turns out that the 1 in the base doesn't contribute, doesn't give you an interesting equation. The 2 in the fiber, so now the 2 in the fiber, that means that now you have 2 parameter family of choices. But if you, again, when you compute with this Lagrangian, there's some non-trivial holomorphic disks. So you need for it to be unobstructed, you need for these disks to cancel. And the equation for them to cancel is exactly the equation for the surface. So that's how this thing appears. And then, I have like a few minutes left. You can do the same thing with the generalization of the singularity to higher dimensions, where again, the fiber is T star Tn. Okay, so of course there's going to be the smooth Lagrangians, then there are going to be the Lagrangians which have singularities that are this singularity, the one we just studied, times some kind of Morse-Bond direction, times a torus. And then there are going to be new type of singularity that appears when you look at C4. Okay. But then that singularity can also be addressed by exactly the same method. So you can just go through all the singularities that appear in that dimension, and each one of them can be handled by the same procedure. Okay, so now let's look at the other space. And again, I managed to screw up my notes. Systematically, this is what happens when you do copy and paste. That y3 there, basically you set it equal to 1. So this is, as I explained before, geometrically, it's a conic bundle over c star squared with discriminant locus along this curve. This curve, by the way, is the pair of pairs. So when you do SYZ duality for this, again, I'm quoting Gross and Matesi and Mr. Bernard, and then my work with Ludmil. When you do mirror symmetry for this and you try to just think about the Lagrangian tori, you get the exact same picture that we had before, except now over the Novikov ring, but let's just ignore that. You get all points except for these kind of coordinate hyperplanes. That's this Zi equals Zj equals 0. They're missing from your space. They're not obtained by smooth Lagrangian. Just as before, if you allow yourself immersed Lagrangians, you get everything except for this one. At least by straightforward construction, it's not clear what corresponds to that guy. That's the origin. So we should be able to fill in the origin. Well, I claim again that there is a Lagrangian in this conic bundle. So let me write it correctly. Which gives you this missing object. How do you get it? So I wrote something there. So Paul Seidel has this inverse Lagrangian here. let me note for interest's sake that it has 3 self-emergent. So this is the pair of pants. It lives on the discriminant locus. So this thing is embedded inside C star squared. And what you can do is you can just fill this by a disk, by a Lagrangian disk. Which is Lagrangian. Okay. If you have a Lagrangian inside C star squared, and you have this conic bundle, then over over a point that is not on the discriminant locus, you can lift and find an S1 inside X. So this X away from the discriminant locus, it's a conic. So this, basically imagine taking the central curve of the conic. So then what you get is D2 times S1. But at the boundary, at the discriminant locus, this gets collapsed. There's some identification. So collapse the boundary. Well, not quite collapse the boundary, collapse the boundary to S1. If you know a little bit of topology, you can just trade this for gluing 2 copies of D2 times S1 together. That's an S3. But this S3 is not embedded. And the reason it's not embedded is that the original Lagrangian we started with had some self-intersections. And these now give you self-intersections of this S3. 3 self-intersections. Why am I mentioning all this? Because the Floer cohomology, of this S3 of itself, well, let's call it L. Okay? It's now going to have, well, the rank of it is going to, well, it's going to be the cohomology of S3 plus contributions from all the self-intersections. But that's just 1, correct sum key 2, correct sum key 3, and each of these VI have rank 2. Every self-intersection contributes a rank 2 to the Floer cohomology. So this goes back to Cahill inverse. Okay, so let's count dimensions. This is 2, this is 6, this is 8. So this is, as a vector space, cohomology of T3, which is exactly what the Floer cohomology of the skyscraper sheet was pointed. Now I actually haven't, in the other case I've actually computed that you get the right module. In this case I haven't computed that you get the right module, all I've computed is that it's actually orthogonal from all the other Lagrangian tori that you've ever built. So it gives you a new object into the chi category. I'm pretty sure that some careful thinking will show that it gives the right thing. So I have this construction. Now you could do the same thing in higher dimensions. I'll stop in a second. But you just replace Seidel's Lagrangian by Sheridan's Lagrangian, because this equation is basically an equation for a pair of pairs. Again, take the last m and make it into a 1, so that it's clear. Okay, so summary slide. So if you look at my work with the Untitled, we basically proved that if you try to understand linear symmetry for supersurfaces in projective space from the SYZ point of view, then you only need these kinds of singularities and their more small versions. So the ones that I just showed appear at the vertices of some kind of tropical construction, and then in higher codimensions you see the things in previous dimension cross with some trivial dimension. So now we know that all such singularities, and maybe we don't have to do Floer theory with them. I mean, maybe people who want to do microlocal sheaves can do some kind of Floer theory with them, but I don't have to do Floer theory with them. But we can replace them with Lagrangians. And since we can replace them with inverse Lagrangians, and since we can replace them with inverse Lagrangians, we can try to run a family Floer cohomology program for this specific class. So anyway, so hopefully this will be, I don't know what you already said, we should try to do this in 4 years. Maybe we'll try to do this in 4 years. Thank you.
Any questions?
So if you go beyond what the double function estimated one of their case, we try to see what is.
Yes, so that I don't have a. So I think the next thing is actually we also have an SYC construction for complete dimensions, and I haven't thought about the geometry of those. That's I think somehow one of the next things that we need to do. I don't think these give, based on what happens in tropical geometry, I don't think that these give the necessary local, all the necessary local models.
This does it, it does that.
I don't think it is. I think there's more. Yeah. So I haven't seriously thought about it.
You have any feeling that all the necessary significant place like mass lump, or you need something?
Yeah, that's a very good question. I don't want to make a claim about all singularities. That just seems too much. But I haven't, yes, I would suspect that the things that appear in mirror symmetry, they're likely all to be obtainable by some ends of inverse things. Because that is what, and this one just happened, we got lucky. This is really a Lagrangian sphere with the right thing. But the other one, it's not. In fact, it's a good question. Is there actually a Lagrangian subman, an inverse Lagrangian submanifold, which represents the other singularity? Because what I produced is a summand of an inverse Lagrangian. I said it gives you 2 points. Now I don't know how to get rid of it.
Other questions? Yeah.
So the fact that the cohomology of the Lagrangians that you add is always porous cohomology kind of uses the expectation that the missing points are smooth points on the other side. Right?
I think you could say that, or you could say it confirms that we should expect them to be smooth.
But which one do you expect?
No, I expect to prove that the mirror is smooth by proving that this lives in a family with. I've had to prove that this lives in a family with the other ones. You see, you want to do family, so this gives you a new point, which behaves like a smooth point. Okay. So now build a family Floer chart like this, and glue it to the family Floer chart coming from the actual tori, and then you will have produced your mirror and prove that it is smooth, without assuming mirror symmetry. That's why I want to find these.
But like, is there any? I mean, okay, I can see that in this case it happened.
Yes.
Like why exactly it happened? Why did you expect to produce this complicated Lagrangian?
I don't have an answer to that. I mean, in the sense that, no, there have been, in this case, again, it's confirmed by a Fuller cohomology computation. You could, in this case, you could just pass it the Rapid-Chi category and compute the Rapid-Chi category and see, you got the right answer. Why do I not like that? Because that's not going to be something that I can put together in a closed symplectic manifold so easily. Okay. Whereas this, it's just going to live inside my closed symplectic manifold once I can take something that has this as a local model. Maybe I do have an answer to the question. But why did I expect it? Because Fuller cohomology told me that it was supposed to be the case. Just didn't have a closed cohomology.
More questions? Thank Mohammed.
How much?